Good morning, students. Today is video number 2. We continue yesterday class. Yesterday class last definition, transitive relation. Today one more definition, equivalence relation. Yesterday, reflexive explained, symmetric and transitive. This is also a type of relation, equivalence relation. A relation R on a set A is said to be equivalence relation on A. A relation R on a set A is said to be equivalence relation on set A if R is reflexive, symmetric and transitive. When you say the equivalence relation, it is satisfying all the three. All the three means R is reflexive, symmetric and transitive. These three conditions are satisfied, then it is called equivalence relation. For example, A equal to 1, 2, then relation R equal to 1, 1, 2, 2, 1, 2, 2, 1. You check whether it is equivalence relation or not. I am taking set A is 1, 2 and R is 1, 1, 2, 2, 1, 2, 2, 1. Now it is reflection because yesterday I explained the definition of reflection. Every element of set A is related to itself. 1, 1, 1 is there, 2, 2, 2 is there. Next, symmetric. Symmetric means what? A comma B, B comma A. So 1, 1 reverse is 1, 1, 1, 2, 2, 2 is 2, 2, 1, 2 is 2, 1, 2, 1 is 1, 2. Now it is symmetric. Now transitive you have to check whether transitive is possible or not. 1, 1, 1, 2, 1, 2 also. Yes, belongs to R. Is there any possibilities? No. 2, 2, 2, 1, 2, 1. This also 2, 1 is there. So 1, 2, 2, 1, 1, 1. So this relation R is equivalence relation. Well, this is a very important definition. Define equivalence relation. Give an example, even 2 marks question, or it may be 1 marks question. Give an example, a simple example, and so many examples possibilities there. I am taking a set A is 1, 2. The relation R is 1, 1, 2, 2, 1, 2, 2, whatever take. But this relation R is satisfying all the three conditions: reflexive, symmetric, and what? Transitive. Okay. So this is the another second example. Example number 2. Yesterday, reflexive, symmetric, transitive, I explained generally. Now, reflexive equivalence relation example in generally. A relation R, a relation R is parallel to in the set of straight lines, straight lines, straight lines, in the set of straight lines in a plane is equivalence relation. This is enough. But in this example, no need of setting. A relation R is parallel to, in the set of straight lines is in a plane, is equivalence relation. When you are taking set A, the relation on A, that compulsory. Without set A, you are taking equivalence relation, that is wrong only. Isn't it? So for example, 1, 2, 1, 1, 2, 2, 1, 2. Without set, you are rating that equivalence relation. You are giving example. That's 100% wrong only. So better alternate two examples. One using set A and without set A. In generally, a relation R is parallel to, in the set of straight lines in a plane is equivalence relation. This is very important. In what this parallel, no, this reflexive, even it is symmetric also is there, and it is also transitive, and all the three are satisfied. This is called equivalence relation. And most important definition, equivalence relation. Okay, what is equivalence relation? It is satisfied reflexive, symmetric, and transitive. The one more important, define equivalence relation is asking, one must be. And no need of loss. Only you have to write the name of loss. Reflexive, symmetric, transitive. This much only. No A, comma A, comma B, B, comma, okay? So only names you have to write. This is the equivalence relation. Next, wide relation. Wide relation. Wide, another name is called empty relation. What is called? Empty relation. This wide is called empty relation. Wide or empty relation. A relation R on a set A. A relation R on a set A is said to be wide relation or empty relation if no element of set A, if no element of set A, if no element of set A is not related to any element of set A. For example, set A 1, 2, 3. A repeating definition, if no element of set A is related to any element of set A, that is called wide relation. So good example I mean, so many examples are there. So I am using set A. A value 1, 2, 3. Now I want an example of wide relation. What is the wide relation? The wide relation R is equal to A comma B such that A belongs to set A, B belongs to, because I told a relation on a set A, both are belongs to set A only. So condition A plus B equal to 10. So this relation is empty, wide relation or empty relation. Why you are telling this relation or wide relation? Because no one sum of these two numbers, no one sum of two numbers is not equal to 10. You see, you take any two elements, you can add, it's not possible. 10 is not comes. A plus B equal to 10 is not possible in this set. So this relation R is called empty relation or wider relation. This is the problem. Yes. No sum of two numbers is not equal to 10. So this is called wider relation. What is called? Wider relation, or it is called empty relation. It is called empty relation. So one more example. this is the 1. So another example, let A be a set. Let A be a set. Let A be the set of students. What a set of students of a boys' school. What a boys' school. Let A be the set of students of boys' school. Then what R is equal to A comma B such that A is sister of B. When I am taking this example, students suddenly they are laughing. Sir, what sir you are telling wrong? Wrong means there is an empty only this. Because in a class only boys class is there. When I attend boys class, the relation R is A comma B. A is a sister of B. A is a sister of B means there are no sister that girls are there, only boys are there. So this is also called good example. This is also called wide relation. I gave 2 examples using set A. Without set A, let A be the set of students of boys school. The relation R is equal to A comma B. A is the sister of B. This is the wide relation on set A. Now I am explaining 2 examples using set A, without set A. Okay? Both anyone had to remember. Then what is next? Universal. Universal relation. What a universal relation. Universal relation, even at the previous one, empty relation I explained, no? Empty is also subset of A cross A. R is equal to empty. R is empty. Empty subset of A cross A. R is empty. Is called empty relation. So it must be subset of what? A cross A. Now it is universal relation. A relation R on a set A is said to be. A relation R on a set A is said to be universal relation if each element of set A, I'll repeat once again, if each element of set A is related to every element of set A, every element of set A is called universal relation. I'll repeat once again. A relation R on a set A is said to be a universal relation if each element of set A is related to every element of set A. That is called universal relation. So if you want one example, suppose A universal relation, for example, the previous example I explained, previous one, that boys school. That's only example I'm continuing here. What is the boys? The difference between the difference between of heights A and B is less than 3 meters. 3 meters means, so all are subset of that what 3 meters only. Okay, this is 3 meters is there. Then boys, another boys. So these are less than 3 meters. So this is called universal relation. Difference of heights A and B is less than 3 meters. So this is called universal relation. I'll explain one more example using set A value 1, 2, 3 and B equal to 4, 5 and R is defined R is defined by R equal to A comma B such that, so if you want to take A belongs to A, B belongs to B. Okay. So what is the EA greater than B? A greater than B. But I am using set A and set B. Yes, set me. R equal to, what is the A greater than B? A less than B I am taking, not A less than B. So 1 comma 4, 1 comma 5, 2 comma 4, 2 comma 5, 3 comma 4, 3 comma 5. Total 6 outputs. When A comma A belongs to B means A less than B, lesser than 6. I think this is called A cross B. So all are present, whatever the A cross B, how many outer pairs in A cross B? 6 are there. So what is the relation R? 6 only. So R equal to A cross B. This is called universal relation on A and B. So universal relations, if each element of set is related to every element of set. Next one, identity relation. What is identity relation? This is maybe it is last definition. Identity relation. A relation R on set A is said to be identity relation. But I said videos 1 I explained that the common word is a relation R on a set A is said to be what identity relation if every element of set A, if every element of set A is related to itself only. But itself only. In a reflexive, every element of set is related to itself reflexive. Be careful. Reflexive identity almost same sentence is there. They are only itself, but itself only. For example, identity relation. Suppose A is equal to 1, 2, 3, the set A. What is the identity relation? Identity relation is denoted by I suffix A. What is the identity relation is denoted by I suffix A. What is the every element of set is related to itself only. Itself only. So only means 1, 1, 2, 2, 3, 3. So this is called identity relation. Itself only. Every element of set A is related to itself only. So my question, is it identity relation or not? Yes. Is it reflexive or not? Yes. This is also reflexive. You remember, every identity relation is reflexive. But reflexive is not sometimes identity. Even you take this 1, 2, this is not identity relation. Identity relation is itself only, but it's not itself only because 1, 2 is there. This is not identity relation. No, it is reflection. So very important. Every identity relation is reflexive, but reflexive is not an identity. So this is the another definition. So how many types relations is over? One is, repeat once again, reflexive, symmetric, transitive, equivalence relation, wide relation, universal relation, identity relation. Okay, so these are types of relations. Then in video number 1, yesterday class, in video number 1, there are also many types of definition I explained. What is it? Order pair I explained, or Cartesian product I explained, relation definition I explained, relation on a set A explained, then inverse relation, then domain range. This much only. This much it is the concept is not more. This is only get around 15, 20. Or yesterday some we said 15, 14 to 15 definitions. So problems that are very important. Students, they know that answer, but how to start that problem? That is very difficult. Okay, they are telling everything. They are telling formula, everything they are telling, but you start replacing means they will not try. So that is the problem. Okay, I will start discuss problems. So one by one. Now problem 1 I will start. Right. Determine whether the relation are defined in the set A equal to 1, 2, 3, dash 30, 40 as R is equal to x, y such that 3x equal to 1 or 3x minus y equal to 0 is reflexive, symmetric and transit. Is reflexive, symmetric or what? Transit. So this is the example, that problem. Determine whether the relation are defined in the set A. Be carefully, set A. 1, 2, 3 up to 14 are given. So what is the defined R is x, y such that 3x minus y equal to 0. See whether it is reflexive or not. He is asking question, determine whether the reflexive, symmetric or transitive. See how to start. So one by one I'll repeat. I'll start. First one is what is? Better we start. What is the defined? R is equal to x, y such that 3x minus y equal to 0. Even both x, y belongs to a set A only. Suppose there are two sets are given. X belongs to A set, y belongs to B set. So x, y such that 3x minus y equal to 0. X, y belongs to A. This is the defined. Now separate, you start. So 3x minus y equal to 0. Y equal to what? 3x. Y equal to 3x. I am thinking that he is given, defined y is tx. Okay. X value 1. Then y value 3. So 3 belongs to what? Setting. X is 2, y is 6 belongs to it. X is 3, y is 9 belongs to it. X is 4, y is 12 belongs to it. X is 5, y is 15 does not belong to it because the set A 1 to 14. 1 to 14 is given. Okay. The relation R equal to order pairs 1, 3, 2, 6, 3, 9, then 4 comma 1 3 2 6 3 9 4 12. So this ordered pair not, because 15 not belongs to set A. Actually both x and y must be belongs to set A only. This is called relation on the set A, not A and B. Okay. So both x and y. X is 1, y. X is 2, y 6. X is 3, y 9. X is 4, y 12. X is 5, y is 15. So does not belongs to A. No, this is called relation. What are you asking the question? Question is asking whether it is reflexive or not. The first one, reflection. Reflection. Be careful. I repeated many times. Definitions. Reflection means A comma A belongs to R. But how many elements are there in set? Up to 14. What is the reflexive relation? Every element of set is related to itself. So for set A is 1 2, 1 1 is not there, 2 2 is not there. Even you take reflexive 1 comma 1 comma 2, 1 comma 1 does not belong to R, 2 comma 2 does not belong to R, so on. 14 comma 14 does not belong to R. Therefore, R is not reflection. On 1 1 2 2 dash dash 14 comma 14 does not belong to R. Therefore, R is not reflection. Now it is enough. 100%. No doubt. Because a related itself is not there. 1 1 2 2 3 3. Okay. But all must be present. It is very important. 2 2 is there, but it is not there. All R must be belongs to in R. So this is not a reflexive relation. Students' questions. Sir, why you are taking 1 1 up to 14? It takes time now. 1 1 14 times 1 1 belongs to 2 does not belong to 3 3 4 4 5 5 6 dash 14. It takes time. So in general, how to start reflexive relation? I told you for E belongs to set A. A may be 1, maybe 2, maybe 3, 4, 5, 6, 7, 8, 9, 10 up to 14. Whatever you can choose. For A comma A, for A belongs to A, so A comma A does not belong to R. It is finished. Previous one, students that every student that 1 1, they don't know that how that definition. 1 1 not there, 2 2 is not there. Okay, no problem. But in generally, for A belongs to A, but A comma A does not belong to R. Therefore, R is not a reflection. Then what is next? No, is it reflection? No. Then what is next? Symmetry. Whether it is symmetric or not. Whether it is symmetric or not. Okay. Symmetric. What is the symmetric definition? One ordered pair is given. We have to prove another ordered pair. What is the one is given? A comma B. We have to prove B comma A. Okay. A comma B belongs to R. But B comma A belongs to R. Then R is called symmetry. Now you take 1 comma 3. 1 comma 3 belongs to R. Some ordered pairs reverse also is possible. But here I am taking 1 comma 3. But 3 comma 1 does not belong to R. Therefore, R is not symmetric. Let's see. No, sir, I'm taking to take. So one example is not symmetric, means why you are taking another? Not possible. Why you are taking another 2, 6, 3, 9, 4, but you are giving example, not the means for. One example you are giving not symmetric, it is enough. Next second one not necessary. Even this also not there. You want to take 2, 6, 6 not there. 3, 9, 9, 3 not there. 4, 12, 12, 4 there. But one example. So this problem is R is not symmetric. Is it reflexive? No. Is it symmetrical? No. Then we check transitive. Transitive what is the relation R? R is repeating, what is the y equal to 3x, sorry, x equal to, what is the y equal to 3x, x1 3, x2 y6, x3 x3 9, x is 4, y is 12. So whether transitive, whether possible or not. Transitive means I explained that A comma B, B comma C. A comma B, B comma C. So 1, 3, 2, 6 not possible because I want A comma B, B comma C. So this must be same one. This, these are not possible. Okay, you don't take this. So 1, 3, 3, 9 S. You take 1, 3, 9. 1 comma 3 belongs to R and 3 comma 9 belongs to R. But 1 comma 9 does not belong to R. Therefore, R is not transitive. R is not transitive on A. Hence, what is? Hence, R is neither reflexive, symmetric, transitive. Neither only. The relation R is what? Neither reflexive, nor symmetric, nor transitive. So this is sometime depends upon marks. Even 3 marks means okay. This is not a and before reflexive you can write relations. Even maybe it's 5 marks also possibility there because you have to find a relation. When you substituting x value, y value, x, then that is also important. And relation you have to find relation you got. So in reflexive, symmetric, transitive, then concluding the relation R is neither reflexive nor symmetric nor transitive. This is the problem. Okay? Given y is 3x, y is 4x, but I given y is 3x. Given sometime y is 4x, y is 6x, whatever it is. Be carefully. So set up to 14 is given. Better even you generally also have to, but reflexive are written no. A comma A belongs to A, but A comma A does not belong to A. Even transitive possibilities, but does not belongs to means next to example is not necessary. Okay, so this is the problem 1. Next problem 2. Show that problem 2. Determine whether the relation R defined in the set defined in the set A 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5 as R is equal to x comma y such that y is divisible by x. Y is divisible by x. Y is divisible by x is reflexive, comma symmetric, or transitive. Determine whether the relation R is defined in the set A 1 to 6 are given. So what is the condition? Relation R is defined x comma y. Y is divisible by x. What are? Y is divisible by x. So we will check whether it is reflexive is there, symmetric is there, or transitive. Then we will start. The relation R equal to x comma y such that y is divisible by x. Y is divisible by x. Another meaning, x divides y. Y is divisible by x means x divides y. So what is the without A cross A? A cross A means 36 order pairs are comes because the set A is 6 elements are there. How many order pairs in A cross A? 36 order pairs. It takes more time. Even that is also 5 takes 3 to 4 minutes. But no need. But without A cross A, we can write the relation R. Y is divisible by x or x divides 1. So what is the possibilities? 1 comma 1, 1 comma 2, 1 comma 3, 1 comma 4, 1 comma 5, 1 comma 6. Carefully, these are y is divisible by x or x divides y. Next, 1, 1, 1, 2, 1 divides 2, 1 divides 3, 1 divides 4, 1 divides 5, 1 divides 6. Then what is 2 divided 2 comma 2, 2 divides 2 is not divisible by 2 comma 4 is comes 2 comma 6 possibilities there. 2, 2, 2, 4, 2, 6. Then what is next? 3 comma 3, 3 comma 6. Then what is next? 4 comma 4. Then what is next? 5 comma 5, 6 comma 6. So this is the 1, 1, 1 comma 2, 1 comma 3, 1 comma 4, 1 comma 5, 1 comma 6, 2, 2, 2, 4, 2, 6, 3, 3, 3, 6, 4, 4, 5, 5, 6, 6. So these are y is divisible by x or x divides x divides. Even you read sometimes the questions are changing, but in textbook y is divisible by x is that x divides y is also possible. Okay, be careful. So this is the relation R. Now you have to check whether it is reflexive, symmetric, transitive. Now you start one by one, whether reflexive or not. I repeat once again. Reflexive, every element of set is related to itself. So what is the set? 1 to 6 is there. 1 means 1, 1 is there. 2 means 2, 2 is there. 3, 3 is there. 4, 4 is there. 5, 5, 6. So what is the first one? Reflexive. Reflexive. Okay? Reflexive. 1 comma 1, easy method. That's okay. Easy steps. 1 comma 1 belongs to R. 2 comma 2 belongs to R. 3 comma 3 belongs to R. 4 comma 4 belongs to R. 5 comma 5 belongs to R. 6 comma 6 belongs to R. Because here all are I'm taking because only 6 order pairs we can have. The previous one 14 order pairs will possible. Up to 14 numbers are there. So it is a very difficult. there are 6 order pairs. Even you can take dash dash, no problem. 1 1 belongs to R, dash dash dash, 6 comma 6 belongs to R. So therefore R is not reflexive. R is reflexive on E. Now it is R is reflexive. Every element of set is related to itself. Is all. But anybody tell me what is generally how to write the reflection generally of A belongs to A belongs to set A comma A belongs to R. It is very simple. You have to select one element in A comma A belongs to R. A1 1 1, A2 2, A3 2, A100. Why are you taking A100? Because set is 600. A7 7 7 is not set up to 6. A6 6 comma 6. This is the reflexive relation. Next one is symmetric relation. Symmetric relation. Even it is called symmetric, symmetrivity, reflexivity. Symmetric, simply. So what is a symmetric definition? You have to select one order pair and reverse must be belongs to R. A comma B belongs to R, B comma A belongs to R. Okay. 1 1, okay. 1 2, okay. 1 3, 1 2 2 1 is there, right? No. 1 comma 2 belongs to R, but 2 comma 1 does not belong to R. Therefore, R is not symmetric. R is not symmetric on A. R is not symmetric on A. Not means it is over. One example is enough. Even I am taking 1 comma 2, some students are taking 1 3, 3 1 is not there, 1 4 4 1. There is no need of all the, okay, this is enough. So 1 comma 2 belongs to R, 2 comma 1 does not belong to R, means this is not a symmetry. Then what is next? Whether it is transitive or not. And it's very difficult because many are their order pairs, but you should check all the possibilities. Okay, not one. You have to check all the order pairs. So what is the next? Transitive relation. Even this is called transitivity, reflexivity, symmetry, and transitivity. So possibilities I am checking. 1 1 1 2 1 2. 1 1 1 3 1. 1 1 1 4 1 4. 1 1 1 5 1 5. 1 1 1 6 1 6. 1 2 2 2 1 2. 1 2 2 4 1 4. 1 2 2 6 1 6. 1 3 3 3 1 3. 1 3 3 0 1 6. Next 1 4 4 1 4. 1 4 no problem. 1 5 5 1 comma 5. 1 comma 6 1 comma 6. Then what is this is called? Transitive. This is transitive. You can take any two order pairs, but transitive you have to select two order pairs, A comma B, B comma C. This okay, this okay. So 1 1 1 1 2 2 2 1 2 1 2 2 4 1 4 1 2 2 6 1 6 1 3 3 3 1 3 1 3 1 6 1 6 1 4 4 1 4 1 5 5 1 5 1 6 8. You can begin. So therefore, for A belongs to set A. I am not taking all this, but it must be belongs to no. It is a transitive. Transitive means how many these possibilities you are taking, so many possibilities are one, these two, these five. No. For A belongs to A comma transitive means how many elements? 3 elements. For A, B, C belongs to A comma B belongs to R, and B comma C belongs to R. It implies A comma C belongs to R. Students are not satisfied. For A, B, C, so whether it is giving marks or not, that thing there. Don't worry. For A, B, C belongs to the 3 elements you are telling. You are taking 2 order pairs. For A comma B, it must be A comma C belongs to R. This relation R, A comma B belongs to R, B comma C belongs to R, A comma C belongs to R. So this is the transitive. Otherwise, what you take, you are not satisfied. I am telling this is okay example. Even you take one example also, no problem. One example. Example. 1 comma 1 belongs to R. 1 and 1 comma 2 belongs to R. It implies 1 comma 2 belongs to R. Therefore, R is transitive. On how many? So many possibilities are. If better we can write generally for A, B, C belongs to A comma B belongs to R, B comma C belongs to R, A comma C belongs to R, and including one example you can write that it is the relation R is symmetric. Hence, what is the last concluding? Hence, R is reflexive. R is reflexive, transitive, but not symmetric. Not symmetric. Not symmetric. Hence, the relation R is reflexive, transitive, but not symmetric. So, what is the problem? Say, Y is divisible by X, or X divides Y. So, this is another example problem. Next, problem number 3. Okay, this problem just I am explaining, so very easy. Determine whether the relation R in the set Z of integers defined as R equal to X comma Y, such that X minus Y is an integer. Yes. This is, I am not giving steps, just orally I am explaining, because it's very simple. Integer property. Difference of two integers, that X and Y are integer, difference also integer. Okay. So what is the first one? Solution. R is equal to X comma Y, such that X minus Y is an integer. What is the first one? The reflexive. What is reflexive? Very important. but here integer is given, set of integer. Elements belongs to Z. Ordered pair belongs to R. So how to start the equivalence relation? Very important. For X belongs to Z, and most of students are taking X belongs to R, but R not R, but this is set is Z only. X belongs to Z. For X belongs to Z, X minus X, what is your answer? 0. 0 is an what? Integer. 0 is an integer. That is X comma X belongs to R. Therefore, R is reflexive on Z. That's simple. What I'm telling, how to start. बहुत सिंपल रहता, स्टूडेंट्स को मालूम नहीं होती कैसा लिखना है. Simple, right? Yes, but it's difficult. I am telling you, easy only, but students, it's very difficult. X belongs to Z. X minus X 0 is an integer. When X minus difference of two integers 0, you are saying it related itself wrong. X comma X belongs to X comma X belongs to R means R is reflection on Z. Now it is reflection. Now what is second one? Symmetric or symmetricity. In symmetry, how many elements are there? 2 elements. How many order pairs are given? 1 order pair given. Which order pair is given? A comma B. What you prove? B comma A. Okay. A comma B is given. We have to prove B comma A. How many elements? 2 elements. For X comma Y belongs to not R, it is Z. These 2 elements are belongs to Z only, integers. If X comma Y belongs to R, it is given. Given means what? X minus Y is an integer. X minus Y is an integer. Also, Y minus X is an integer. How you are asking? So properties, integers. Y minus 3 is 2 answer. 3 minus 5 is minus 2 answer. 5 minus 2, 3 minus 5 is minus 2. Both are integers. So X minus Y is integer. Y minus X is also integer. Therefore, what is Y comma X belongs to? There is Y comma X belongs to R. Therefore, R is what? Symmetric on Z. Simple. X minus Y is an integer. Also, Y minus X is an integer. Y comma X belongs to R. You are taking X comma Y. You have improved already. Given a reverse also is integer. Okay? Now it is symmetric or not? Yes. This is symmetric. And what is the next? Transitive. Transitive is possible or not? Transitive number 3. Transitive. Even this is also called transitivity. How many elements? 3 elements. Yes, correct. 3 elements you have to select. How many order pairs are given? 2 order pairs. X comma Y belongs to Z R, and Y comma Z belongs to R. Here Given two order pairs, we have to prove third order pair. A comma B, B comma C given, we have to prove A comma C. So here I am using x, y, z that given. X comma y belongs to y comma z belongs to. Now it implies, what is the x comma y belongs to our definition? It defines x minus y is an integer and y minus z is an integer. Even x minus y is integer, some this value you take k1, even this is also k2. Okay. Now a x minus z, this x minus z can be written as x minus y plus y minus z. X minus y is already integer you are telling. This also you are telling integer. Even you call this is k1, this is also k2. k1 plus k2. Even this is x1, x minus y. X minus y is k1. Y minus z is k2. Now x minus z equal to x minus y because y cancel x minus z. It can be written as x minus y plus y minus z. Even the y cancel, no, this x minus z comes. So what this is? An integer. For example, k1. Then what is this is? k2. k1 plus, this better be called x minus k1, this is k2, this is k1 plus k2. And sum of two integers is again what? Integers. So is an integer. Is an integer. So x minus z is an integer. It implies x comma z belongs to R. Therefore, R is transitive on Z. This maybe it is a standard problem only. In CET, the relation R is defined. R is equal to x comma y. So that x minus y is an integer. 4 options are given. So first we have given it. So this problem is satisfying all the three. This relation, this R is the relation R is reflexive, symmetric, also transitive. Hence the relation R is equivalence relation. But he is not asking equivalence relation. Determine whether the relation R is symmetric. R is symmetric, hence the relation R is symmetrical, reflexive, symmetrical, and what? Transitive. When the question is asking that show that so that the relation R is equivalence, means you have to write. Now satisfying or reflexive, symmetric, transitive. But this relation R is equivalence relation. What is the equivalence relation? It is satisfying, reflexive, symmetric, transitive. And today's equivalence relations, wide relation, universal relation, identity relation, then problems I had discussed. One problem y is 3x I explained. Another is y is divisible by x. Second problem I explained. Then another is x minus y is an integer. So thank you. Continue next video. Already theory parts is over, and continue the problems. Okay, you are enjoying. It is not the difficult problems. So I think only that reflexive, symmetric, transitive, equivalent. This much only. Thank you. 예, ಅದು ವಿಡಿಯೋ 예, ಅದು ಇನ್ನೂ